My student number is 32456-324. My name is Camilla Eliott and I declare that this is all my own work. I strategically made the rectangle bigger and recorded my findings. The relationship I found was the difference going up in ones, but this was only a conjecture as the relationship ended at 5, as you can see in the tables that I made up. I looked at bigger squares this time. This is a 5 by 5 square and the amount of squares within it is 55. As you can see, these actually correlate with 1 by 1, 2 by 2, 3 by 3, 4 by 4, and 5 by 5. The relationship I found was that the dimensions plus all the numbers below it squared will give the amount of squares in a bigger square. A formula to represent this is x squared plus x minus 1 squared plus x minus 2 squared plus ... x minus x squared is equal to the amount of squares inside a square grid with the dimensions of x, y. After making this conjecture, I tried it with multiple numbers from 2 right up to 9. The same relationship occurred in all of these numbers, so I can justify that this is the case for all other squares, whatever the dimensions. This relationship will only happen for squares. The requirement is for it to be for a rectangle. Now I am aware of the square relationship, I can find out the relationship for more columns added to the square. I looked at a simple 3 by 3 square, and how adding a column would change the numbers. This 3 by 3 has a total of 9 1 by 1s, 4 2 by 2s, and 1 3 by 3. In total, it has 9 plus 4 plus 1, which is 14. If I add an extra column, I have 3 extra 1 by 1s, 2 extra 2 by 2s, and 1 extra 3 by 3. In total, it has 20 squares. I added a second column and again it increased in multiples of 2, which is the amount of extra columns. Using this theory of going up in multiples of itself, I tested the 3 extra columns in which the numbers went up in 3, and 5 extra columns in which the numbers went up in 5s. Therefore, I can make a generalized statement that this is also a relationship, shown by the formula, where n is equal to y minus x when x is smaller than y in an xy dimension rectangle, n plus 2n plus 3n plus ... xn is equal to the squares in the extra columns. By finding these two relationships, I combine them together to get a formula to find out the amount of squares inside a rectangle. Basically, it is the square relationship plus the columns relationship added together, which is x squared plus x minus 1 squared plus x minus 2 squared plus ... x minus x squared plus n plus 2n plus 3n plus ... xn is equal to the amount of squares in a given rectangle. In summary, there is a direct relationship between one large square grid and the numbers of squares within it, being the square of itself and all the numbers beneath it. The second relationship is that every column added goes up in multiples of itself, which added together will give the amount of extra squares. By adding the two gives one formula to solve the amount of squares in any given rectangle, which can be shown below. To adapt to a classroom, I would first focus on the square relationship. This makes it easier for year 8 to 9 level, depending on their ability to recognize square numbers and the patterns. I adapted it this way so that students had an opportunity to search for the square numbers. But first, I would begin by showing them these. First, I would ask them about a 2 by 2 square, ask them to find all the squares they can see and write them in a table, and again, show them a 3 by 3 square and ask them to write their findings in a table again. In the student task, they will receive a 4 by 4 square and a 5 by 5 square in groups of 3 or 4. The first group to correctly give the amount of squares within the 2 squares given will win against their classmates. They only have 3 chances to get the answer right. To win, the students must show their working and problem solving on a sheet of paper, indicating the dimensions of every square they found. The second part of the task requires the students to try and find a pattern between the amount of squares and the dimensions of the squares. Using the pattern they find, they must predict how many squares within a 9 by 9 square. They have 35 minutes to do all of this. In regards to the Australian curriculum, problem solving is when the students are in groups to find out how many squares are in the squares they've been given. The focus is on the students identifying a pattern. It gives the students the option of how they wish to investigate how many squares are inside the square. Reasoning is guided by writing down the dimensions of all the squares they find. Also, the demonstrations at the beginning of the lesson should help the students with their reasoning. It gives the students a chance to find a pattern, reason it, and apply it to different situations. It also gives the students a chance to use many options to prove the pattern they found. Students will probably find a few different solutions. The most probable answer may be that the amount goes up in square numbers, all added together. Or if they go further, they add 2 to the difference every time it goes up. The main issue with this task is that students may struggle to count all of the squares they see. This will make it difficult to find a pattern. If they are finding it difficult to see all the squares, one-on-one teaching is probably required to fully understand the concept of the investigation. If students appear to be struggling, I may give them the answer for a 6x6 square and a 7x7 square to help them find the correlation. An extension of the problem could be to have the students create a formula to find the amount of squares inside any given square. At the end, discuss students' findings and compare, making judgments of why this is so.